Hi, everyone. Let's get started. So my name is Will Crichton. I'm a sixth-year PhD student at Stanford, advised by Pat Hanrahan and Manisha Agrawala. And my research is generally about applying cognitive science and PL theory to design better tools for programmers. And as a part of that research, I spend a lot of time not just doing research, but talking about it. So I've talked about PL concepts in blog posts and papers and lectures, and more recently, a lot of tweets. And in trying to communicate PL concepts, I necessarily think a lot about questions like, how does someone come to understand something I'm trying to tell them? Which is really tricky if you think about it. Like, what cognitive processes drive comprehension? And so as a case study in these questions, let's say you wanted to learn more about the theory of WebAssembly. So the canonical paper about WebAssembly was published at PLDI 2017. This is an inference rule from there. And let's say you wanted to understand how loops were type checked. That's what this rule is doing. So you go to the figure, you find this rule. How do you understand it? Well, first, you need to understand the symbols involved. So you might ask, what is C? And then somewhere in the text, you'll find an explanation that says what C is. And then you're going to say, what is TF? And that'll have a separate explanation elsewhere in the document. And you keep going. What is label? And there's another explanation somewhere else. All of these scattered around the document and certainly nowhere near the inference rule. But these are also just the basic questions. Once you get to the trickier questions, like why is T1 the thing in the label and not T2, then that's more of a design question, a correctness question. And there's yet more text in a different part of the document explaining the design decision. Or worse, imagine you never learned PL theory at all. And you're like, what the heck is this big fraction or the sideways T? Good luck Googling any of that, right? And so the point is that by thinking a little bit about these mental operations, we can already see how the standard paper medium doesn't necessarily make it easy to understand PL concepts. And then we crank it up to 11. You know, that WebAssembly rule was easy to understand, but advanced PL papers just have giant impenetrable masses of symbols like this one about cubical agda. There are more fun rules. I'm sorry, Joe, where I didn't get to add yours in the paper due to time, but you should check out the Twitter thread where a lot of people shared fun, large inference rules. Anyways, they're complicated and, you know, exacerbate the challenges in the prior slide. So the key question I've had for a long time is, how can we better communicate PL concepts? And in particular, how can a medium facilitate that communication? And I focus on a medium for two reasons. The first is that expert PL researchers are generally not expert communicators or educators. And if we give them technology to communicate more effectively without significant training, yeah, I think that's a lot more practical than trying to get everyone to take classes about visual design and learning science and whatever. But second, I think there's a ton of low-hanging fruit in the medium because PDFs and LaTeX are just these stagnant technologies that have really not innovated in the last 20 or so years. And so the time is ripe for something better. And so to start tackling these questions, I'm going to articulate my basic principles of an ideal medium. So the first is that all concepts that are used should be linked to their definition. So in PL papers, they use a ton of symbols, a lot more than a person can keep inside of their working memory. And so it's inevitable that a person won't immediately recognize every symbol used in a rule or a proof or something. We use jump to definition in our IDEs for much the same reason. Actually, a really cool example of this is the HTML version of the WebAssembly specification. So every rule is, like the loop typing rule, accompanied by an English translation of the rule, as well as these little links. So if you click on like block type, it'll jump directly to the part of the grammar that explains what a block type is. So that's a fun thing to check out. The link is obscured at the bottom right, but you can find it later. The next principle is that information needs to be kept in context. So with PDFs, related information gets scattered all around a document. And without printing it out, it's hard to compare formalisms with their explanations side by side. And a really good model of this comes from whiteboard lectures. So this picture is me from several years ago explaining product types in Stanford's PL course. And I really like using each whiteboard to contain reference information that students can look back to if they forget the syntax or semantics of a particular concept, by always having that available to keep the information in context. And the last principle is that a common issue with powerful mediums is that people abuse the expressiveness. So for example, when given the third or fourth dimension, it's very tempting to do things like explain sorting algorithms with a GIF. And it's fun, it's eye-catching, it keeps the kids engaged. But there's a lot of research showing that static visualization, unrolled in time, is generally more effective for actually teaching how things work. And this is because the mind is very good at comparing things side by side, but much worse at comparing, say, a current image in time versus a previous one that you may have already forgotten. And so now, grounded in these three principles, I'd like to show you my prototype for the paper of the future. So this is the first few sections of a paper I'm currently working on about program slicing in Rust. The content is not particularly salient, but I'll just walk you through the high-level demo. And as a part of this paper, I have to introduce Oxide, which is a formal model of Rust. So let's scroll down there. All right. So I want to walk you through how this medium changes the nature of communicating concepts about Oxide, a formal programming language. So to start, Oxide has an abstract syntax defined through a context-free grammar. So this defines both metavariables like pi and rho, as well as possible forms for each kinds of syntax. So by the first principle of linking definitions to use, this grammar is available for every usage of these symbols in the paper. So for instance, if we scroll down a little bit and we zoom in on some piece of text, so this is a concrete piece of syntax and unique rho tau, which is the type of a reference in Oxide. We can click on this to learn more. So what is unique? I click and I get something that tells me, oh, unique is part of the ownership qualifier. So that's pretty cool. And a few things to note about this. First, the default is to show information without changing the viewport by using the tooltips. And that adheres to our second principle, where we try to keep information in the context where it's being used. But if you want to jump to the definition because you want to see the definition in context, you can double click this and it'll jump up to where that was defined. Now, watch again. If I double click it, you'll notice a subtle yellow flash on the little unique, the thing that you jump to. That helps you attend to the correct element after you've changed that view, rather than like hunting around the PDF frantically to find that thing. You just click the hyperlink, which is a frequent experience that I have. So that's a nice little interaction. And additionally, if you have these compound forms, so for example, unique is part of this broader form of an ampersand type, then we can use these stacked tooltips to differentiate different levels of the syntax. Or as an alternative, if you hold Alt, you can actually expand out these terms and get a little diagrammatic version of these boxes drawn around each part of the term. That kind of shows you the hierarchy. And then finally, the same definition use mechanism is used extensively throughout the document. So for example, if you see a citation, so like Weiss et al. 2019, if you click on that, you'll again get a tooltip. If you double click, you'll jump to the bibliography and get the little yellow flash on the place that we just jumped to. And so the nice part is we can reuse this definition use mechanism for many different kinds of defined things and get all of these features each time. We also, for example, get the same thing for sections, although we don't have previews since there's a little too much content. Another cool thing is that if you use this system with figures, then you get these same features. So for example, this is a figure defined in HTML, not as a PNG, and it's a little syntax diagram. So it quickly tells you through an example program what all of the different meta variables are and what kind of concrete things that they correspond to. So this is a good diagram by our third principle in that it tries to lay out more information for you at once, rather than say like asking you to click on each thing to figure out what it is. But if there's something in this diagram that is unlabeled and you want to learn more about it, then you can click on it. Like, what is R? Well, R is a concrete provenance, and it's part of these broader expressions. And so, again, the definition use system extends to things like figures, and therefore you can still use those same features. Okay, so the next feature I'll show you is inference rules. So as we've seen, a common pattern in PL papers is you have an inference rule full of Greek accompanied by a natural language explanation elsewhere in the paper. But the problem with that is there's a gap between the information and where it's being used. It's not being kept in context. And so instead, we can use a simple toggle interaction like this to enable these explanations to be directly co-located with the symbols that they explain. And so if you want to get a high-level intuition for what this rule is doing, you can read the English, and then you can get the formal explanation of each part individually. Like, what does it mean for pi to be unique safe? Well, it corresponds to this judgment that you can read more about. And you can also jump to the definition of that judgment if you wanted to, for example. All of it works together. Now, this interface does violate the third principle a little bit because you can't see the symbols and the labels simultaneously. I'm still working on the ideal UI, but it still goes towards bringing the information together into one context. And one other quick feature to show is down here. So here I'm trying to draw a correspondence between an intuitive idea in natural language on the left and a formalized version of that idea on the right. And so I can use these colored underlines to indicate which pairs of things relate. So like here, a mutation intuitively formally corresponds to this like update in the sigma heap or something like that. And this is augmented with further interactions. So if you hover over one of these things, you can see the other colored objects get highlight, or kind of the size of the bar increases to draw your attention, just again, to reduce the amount of work you have to do to draw connections between these two things. All right, back to the slides. So that is a whirlwind tour of my paper of the future. So again, the key ideas are that we link definitions to use and we keep related information close together. And I hope the demonstration has convinced you that there is A, better methods to communicate PL concepts than just using PDFs, and B, that these methods are possible today. But possible doesn't mean easy, right? I mentioned earlier that it's equally important that this style of communication be accessible to any researcher, certainly no harder than it might be in LaTeX. And so let's take a quick look at how this was done. Now, underneath this demo are two key technologies. The first is the browser. So you probably noticed that was in a web page, hence it's implemented with HTML, CSS, and JavaScript. And the second technology is a library I created called Noda. And the goal of Noda is to create a paper authoring experience that has similar primitives to LaTeX, but leverages the browser for a more effective reading experience. So for example, here's the implementation of one section within Noda. So this is using the React flavor of JavaScript. It looks a lot like HTML, but there are custom tags like subsection and definition sprinkled around. To get support for LaTeX symbols, we use the $sign tag, which calls out to Kotek. And then all the logic around tooltips and links is actually handled behind the scenes. The author just needs to tag sections with metadata. So for example, here we say definition, name equals text : TC. And so this shows that this piece of text is defining the type checking judgment. And then anytime we refer back to the type checking judgment, it automatically will link back to this section. Noda handles all of that for you. So to me, this actually doesn't look too bad. And I would know I wrote 2 different documents using this framework. And I actually think that other researchers could use Noda to write real research papers. Now, I'm not going to defend this specific syntax too fiercely because it is a prototype. I've worked on it for 2 weeks and so on. I think the embedded LaTeX strings here are kind of gross, and there are definitely some more nice syntaxes or macros one can make the language simpler to write. But overall, I'm making these 3 arguments ordered roughly in terms of how contentious they are. First, there are better interfaces than PDFs for communicating PL research. I don't think most of you would disagree. Next, specifically, the browser makes sense as the future of PL papers and probably academic papers in general. I mean, it is the world's most powerful GUI system. But what then should be the LaTeX successor for the browser? Now, having done a lot of web development myself, I personally like JavaScript, and I think that the language and its ecosystem are fertile ground for further work. There are, of course, other perspectives. In a mildly scathing review, Shriram said he was desperately torn between cheering on my ideas and loathing the execution. He felt that Scribble, the Racket DSL for writing documents, would be a better fit for this case. He wrote in his review of my paper that Noda is like an irregular quadrilateral being called a wheel. So, I don't know how Scribble is designed to deal with the interactive aspects of documents, but I totally agree. It's important to consider different alternatives. Noda is definitely not the end all be all. But overall, I would say this experiment was a rousing success. Noda got an overwhelming reception on Twitter. Hold on, you can't actually see the counts. It's very important you understand this. This tweet got more attention than the rest of my research combined. Now, maybe that's a statement about the rest of my research. I'll leave that for you to decide. But my takeaway is that a lot of people are excited about this idea. They're ready for the next iteration on PDFs and LaTeX and whatever else. And I also think that the PLHCI community, places like Hatra, are a perfect place to incubate ideas like this. So thank you for listening and happy to take any questions.